In this video, we are going to introduce you to Chapter 4, our next model of motion, and it's the constant acceleration motion model. Okay, so we're going to model this kind of motion, constant acceleration. One way to wrap your head around Chapter 4 is to realize that it's just an expansion of Chapter 3. So let's take a quick look at Chapter 3. Chapter 3 was our constant velocity model. As a reminder, we defined what velocity was. It's my change in position, known as displacement, with respect to time, miles per hour. This ratio is what's constant. So when we say constant velocity, our velocity is constant, but what is velocity? It's a ratio of displacement relative to, or the ratio of displacement to time, where this time is the time over which that displacement occurred. Another way to model this definition of constant velocity is to look at it through a graph. And we noticed that if I take that position, which is x, delta x is displacement, right? The change in position. If I plot my position on the y-axis and my time on the horizontal axis, this assignment of axes is helpful because now we go from a physics definition, or the physics definition corresponds to some graphical characteristics. What is that? Well, the delta x is a change in x, but if x is on this axis, then the delta x on the graph actually is the rise, and the delta t is a run. So if we plot this, and so if we say I have constant velocity, what does that mean? That means my rise over my run is constant. So on a graph, the only shape with a constant rise over run is linear. So I must get a shape that looks like this. It doesn't have to start at 0, but let's say, so I start somewhere, but I get that. So the phrase constant velocity maps or describes two things. Mathematically, it's a ratio that's constant. Graphically, I could picture it as x and t must be related linearly because the slope, the rise and the run, that ratio of rise to run is constant. So the slope of that graph is v. Then, over that same time, I could now plot velocity versus time. We practice this in the worksheets and in the homework. Definitely in the worksheets. I have my velocity is constant. What do I know? What can I tell about it? If this is a slope, the slope is positive, and it doesn't change, right? Because the slope of a straight line doesn't change. So my slope must be positive, so I must be up here, not down here, and I get something like that. The other thing we got from Chapter 3 was that the area of this graph actually meant something or corresponded to something. And it turns out, we found out that the area under, I'll just say area. If you hear me say area, it's always area under. Area corresponds to my delta x. And if you don't remember why, just review your notes, maybe look at the examples, the lab that we did. You practiced calculating area and you saw that it matched how far you were displaced. Okay? By way of review, again, I'm not going to write it out, but the slope of this graph tells you the value of this graph. The area of this graph tells you the rise on this graph. It doesn't give you the ratio, but it does give you the rise. Okay? And if you're not sure why, come see me during academic support. Okay, and we'll go over that. All right. So this is what we're going to borrow from Chapter 3 as we move into Chapter 4. And one way to get into Chapter 4, remember I said it's an expansion of the motion. So the key condition, what's the key constraint here? Constant velocity, right? So for some delta t, my velocity is constant. So the first expansion we're going to do is we're going to break that constraint. We're no longer going to require constant velocity, but we're also not going to try to model any kind of crazy velocity. So what we're going to do is the following, and we're going to go with this, because this is the one way to really figure out or to wrap your head around what this world entails, what it includes and what it doesn't exclude. So the simplest way to expand this model is to allow velocity to change. So we're going to consider, or we're going to allow v to be changing. Over some delta t. Now we're not going to be, now that really opens it up, right? I could have a velocity that's going bonkers. 20 meters per second down to 30 meters per second, or up to 30, then to 28, then up to -5, and then back up to 100. Or it could be changing really smoothly, okay, and be maybe imagine a swing, right? You could think of the velocities of that, right? But it turns out that's a lot. We have many motions. A lot of our motions can be broken down into a simpler change. So the way we're going to change it is we're going to add a little condition that makes it helpful, linearly. And that might not be the best word right now that I'm writing it, so if that throws you off, don't worry about it. But one way to think about it is just to look at the possible pictures. So here's our boundary condition, or the world we're going to live in now. We're going to get out of this world. We're going to make a slightly larger world. But the world we're going to live in looks like this. We're going to allow velocity to start at some point, but to increase or decrease. So now, this is why I knew I was going to draw this, so that's why I used the word linearly. But what we're going to do is we're going to allow velocity to change like this. Okay, well, you see this graph? It looks a lot like that graph. And if I put velocity on the y-axis and time on the horizontal axis, and we're just going to say, let's just deal with this kind of motion. How does everything change if we allow this, right? So it's an expansion of this, but it's not, for example, and I'm going to erase this. It's not something like this. Or it's not that. It's not sinusoidal. Remember the rocking back and forth? Kind of might look something like this, okay? So it's not that. So we're not going that crazy. But we are going like this. Now, first comment is, okay, that's nice that we expanded it. We're now going to allow velocity to change. Is that an interesting model? Long story short, it actually captures quite a bit of the motion that we do day in and day out. For example, classic BMW commercials. So I'm going to erase this as well, but just as a talking point. We do things like this. Imagine your velocity change. I'm going to go from 0 to 60 miles per hour in 5 seconds. Now, if we did that regularly, what does that mean? Linearly or evenly? Maybe that's a better word. Evenly. What do I mean? Well, at 1 second, I must be at 12 miles per hour. So imagine a speedometer, right? Increasing from 0 to 60. At 1 second, I'm at 12. At 2 seconds, I'm at 24. 3 seconds, I'm at 36. 4 seconds, I'm at 48. And then at 5 seconds, I'm at 60. Right? That's an even increase in velocity, 0 to 60 in 5 seconds. And it turns out a lot of our motions that we live with day in and day out are sufficiently, and this is actually what happens, long story short, okay. For a lot of our motions, we have regular increases or even increases in velocity with respect to time. Okay, so if this is going to be the motion we're going to look at, question is, how do we take these ideas and apply it to this? Well, just look at the pictures. Not so much the math. Look at the pictures first. I have xt, the slope is meaningful. I have vt, but look at the line. A line has a slope. I wonder what that is. Okay? Not only that, whatever this is, remember how the slope of this graph is the value of this graph? It means I could also graph the slope of this thing. And what shape should it have? Well, whatever that slope means, it's got to be constant and positive. So it's also constant and positive. So we have the same shapes. Okay? Not only that, we could ask, what's the area under this graph? What does that mean? We already know what the area under a VT graph is. The area is a displacement. We have a different V shape now, VT shape. It's not flat like this. We'll get to that in a separate video. But the world we've now entered is a VT graph where the velocity increases at a constant rate. So what's the slope? And then that slope, whatever it is, it's constant. So I get a line. If the slope's negative, right, I get a negative line. All right, so let's look at the slope. Well, V is the rise. So that's dv, that's delta V, and this is delta T, the run's down here, just like this graph, right? Delta T is the run, delta vertical axis is the rise. The vertical axis here is velocity. Well, what's that ratio? We're going to call that acceleration. And that's where how I quickly got those numbers that I drew, right? 0 to 60 in 5 seconds. What was my change of velocity? 60 miles per hour. And I did it in 5 seconds. 60 divided by 5 is 12. So the ratio, just like this one, when I say constant acceleration, what's constant? This ratio is constant. Hopefully your brain is seeing how starting to pick up on how these two sides of the board are really the same thing. This is chapter 4 stuff, that was chapter 3, but we're using the same ideas, right? So we now have velocity, and we figured out what the slope is. It's actually my acceleration. Something I can't overstate enough. The word accelerate in physics, accelerate, in physics does not mean speed up only. Okay? Accelerate in physics is literally this ratio. So sometimes the result will be that you speed up, sometimes the result will be that you slow down, but both of those, if I speed up or slow down, I accelerate in physics. Okay. Let's continue taking chapter 3 and mapping it to chapter 4. If this is velocity now, and over here in chapter 3, the slope of this graph is the value of this graph, then the slope of this graph is the value of this graph. Well, what's a slope? It's my acceleration. So you now have a new graph in chapter 4 that's worth talking about. We could have talked about this acceleration time graph in chapter 3, but it's boring because if my VT graph is a line, my acceleration is 0. It's kind of trivial. Now, and my acceleration is not 0. Okay, from the 0 to 60 in 5 seconds, my acceleration would be, what, 12 miles per hour per second. Okay, the area under this graph, let's just borrow from chapter 3. xt, vt, slope of x, value of t, area of v is delta x. Switch out the letters. Slope of vt is this value, a. Slope of vt we're going to call acceleration, different word, but it's just the value of my AT graph. Area of AT graph must be delta, why is this delta x? Because the area of this graph is the change in this graph, right? Where the graph where I got the slope, where I got this value. So the area under my AT graph is delta V. Notice, just like I reminded you here, there's no time value, right? This is just the area under this is my rise on this graph. Or just the rise on this graph, or if it's negative, then it's a decrease, or it's in the negative direction, okay? So that's chapter 4, okay? We now have the idea of what acceleration is. We have an equation for acceleration. And just like we called this average velocity, this is really average acceleration, okay? So, but it's the same idea. And let's take care of units as well. Last thing. The units on this one. When we took this ratio, the ratio itself is meters per second. Now I'm going to put brackets around this to emphasize that I'm talking units, but you don't have to write brackets, and sometimes if I forget brackets, I forget them, but in this discussion right now I want to emphasize that we're talking about units, so I want to make it look different, okay? This is meters per second, right? And when I found my area, my delta x is just going to be meters. Okay, let's talk this guy. If you look at the equation, I've got a delta v over delta t. So if we look at the units of acceleration, by definition, it's the ratio of velocity to time, so I just look at the units. The units of velocity are meters per second, miles per hour, right? Meters per second. And time is also just seconds. So the units of acceleration are literally meters per second per second. Traditionally, though, if you put on your UDA lens, what is this? This looks like scratch work. This looks this is a meter per second, but I'm dividing by seconds. So you should realize mathematically, with that seconds in the denominator here, in this big fraction, it's like I'm multiplying by 1 over seconds, right? Meters per second times 1 over seconds. That thing is the same as taking this one, meters per second, and dividing by seconds. So that's what that is. That's what that looks like. And because you could rewrite this is the equivalent of this product. And because of that, we see seconds on the bottom. So mathematically, or UDA-wise, this is equivalent, meters per second, or you could write meters per second squared, and those will mean the same thing. Traditionally, meters per second squared is more frequently used, okay? The reason I want to make this connection is I also want to let you know that if you write this, you're still correct. The reason I want to emphasize this is because it gets you to think of velocity per time, v over t, meters per second per second. This version also, every now and then a student will get mixed up and they'll see seconds squared, and for some reason they think that means the mathematical operation of multiplying time. And then they start using math that we never really derived or doesn't quite mean anything. So that's why I offer, or I remind you what this convention really means. This meters per second. For every so many meters per second, this much time goes by. Okay, it's a little harder to think about that if you see seconds squared. And that is the beginnings of chapter 4.